Hey everybody, thanks for attending tonight's webinar. Scott, you can let me know if my audio isn't good, but assuming it is, tonight we will be covering functions and a little bit of sequences possibly. I will be focusing mostly on the function component and doing some kind of basic functions at this point. I definitely see some new names here, so Scott and I are very excited about that. And additionally, for some of you who are already using the course, you know that we recently switched over to our new platform, and it's a really exciting time for Scott, I, and Target Test Prep. And any of you who have not tried our course or maybe have tried it on our old website, we definitely welcome you to try it out. Right now, there's the link to the course. I can put it in the chat box. It is beta.targetgmat.com. We're going to be switching over to our old URL, targettestprep.com, soon enough. But we've spent a long time creating this new website. We really feel like, as I'm sure most of you know, this kind of takes GMAT Quant to the next level, and we're really proud of it. And it goes along nicely with how we teach these webinars. As I'm sure most of you have noticed, we do very specific webinars on very specific topics, and our GMAT math curriculum goes above and beyond that. You know, the course itself has about 3,000 practice questions to go along with some really, really detailed chapters. So for any of you who are interested in checking it out, you can go to the link I posted in the chat, and let me post it to everyone. And if you have any questions, feel free to reach out to Scott or myself. You know, we're both at Jeff at Target Test Prep and Scott at Target Test Prep. And, you know, we'd be happy to walk you through, you know, our curriculum, how to use it, et cetera. So with that said, we can get going tonight with functions. And the first thing I want to talk about, because I find that students generally don't really know what a function is when they initially get into it, because the way functions are presented on the GMAT is there's a lot of algebra used in them, a lot of unknowns, a lot of equations and things like that. But the essence of a function is that it's something that can be graphed, graphed on the coordinate plane. Now, we're used to graphing on the coordinate plane when we're using and doing things with coordinate geometry. So an example of a function can literally be any equation, but a good example of a function is something like you could see f to the x equals x squared. Now, what we like to call this value inside of the parentheses, it's called the input. And that's actually the x coordinate in in your XY coordinate pair. This is called the output. And this is actually the y coordinate in your XY coordinate pair. So if we were to set up and make a T-chart, and this is maybe bringing some of you back to, you know, late middle school when you did a lot of graphing of these, we can set up a chart and actually do some input and some output. Now remember, the input is the x coordinate, and the output is going to be your ultimate y coordinate, and we can put any value we want in for the input. So let's say we want to start with -2, go to -1, go to 0, go to 1, go to 2. So if we put -2 in for x, we see that the output is that squared, so the output is 4. If we put -1 in for x, we see the output is a +1, working our way down, 0, and then 1, and then 4 again. So ultimately, if we were to graph this, we would graph the points -2, 4, -1, 1, 0, 0, 1, 1 again, and then 2, 4. And what you're going to find is that this graph, and of course I'm just doing this freehand, this graph actually creates what we call parabola, which is kind of a U shape. So if we were setting up our graph here, we could basically plot our points in freehand, and you'll see it's going to look something like this. Now, the good news, everyone, if you do have to graph something on the GMAT, the booklet that you're provided does give you graphing lines. So, obviously, I think it makes sense to take advantage of that. That way you can be more precise in your graphs. This isn't to say that you're going to be forced to have to graph a function on the GMAT, but with that in mind, I think it's always helpful to know what a function is and where it comes from. Most of the functions that you're going to be seeing on the GMAT are a little bit more algebraic in nature, and that's where we're going to start tonight. So, with that said, I'm going to put up the first question, and as always, feel free to enter your answer into the chat box, and I'll give everyone a few minutes, and we'll go from there. Okay, I see we have a few answers up on the screen, and so we can go through this. So the name of a question like this is called a compound function. So, technically what we're doing is we're taking the function equation of h to the x, and we're using an input of 36. And the first thing we're going to do is we're going to get an output for that. So we're being super technical here. We're saying h to the 36 equals the square root of 36 minus 2 over 2. Now, if we do that out, that gives us 6 minus 2 over 2, or a value of 2. So what happens is we then take the output of 2, and we say, well, now we need to get g to the 2, where 2 is now becomes the input. So when we plug that in, we have x to the 3, which becomes 2 to the 3. We add 1. 8 plus 1 is 9. So, more or less what a function is it's kind of like following directions. You're given very explicit equations, you're given very explicit input, and you have to substitute in using that. So presuming, you have no issues following that, a question like this shouldn't be too bad for you. Now, I want to give everyone one more version of a compound function. This is where we're going to have the same function equation, but we're just going to be using it twice. So I'll give everyone a few minutes again, and then we can go from there. Okay, so similarly to the last question, as you can see, this is another version of a compound function. The function equation f of x equals x plus x squared over 3x is the equation that we're going to be plugging our input into. So we can see we start with f of 6. So obviously 6 is the input. We're going to plug that in. 6 plus 6 squared, which is 36 over 18. And of course, we can reduce this down just a bit. 3 goes into 36 12 times. 3 goes into 18 6 times, so we get 12 over 6. Of course, 18 just goes into 36 twice, so it doesn't really matter. But that's 6 plus 2, and that's 8. So what we have now is we have 8 as the output. So we take that output, and we're going to say f of 8 now, and we're going to do the math there. So the difference between this problem and the last one is that in the last one we had 2 function equations. In this one we only have 1 function equation that we're going to reuse twice. So when we say f of 8, we have 8 plus 8 squared over 3 times 8, 8 plus 64 over 24. Now, I had mentioned this last time, and it's worth bringing up again. You know, I don't ever want anyone to get nervous if they see they have something like this. Not until you look at your answer choices, because a lot of times we'll jump to conclusions thinking that we potentially did something wrong, but as you look at your answer choices, A, B, C, D, and E, you're going to see in all of those you're dealing with fractions. So that means you're probably doing something correct rather than doing something wrong. So the last thing we want to do is we can get common denominators after reducing the 64 over 24. Or actually, there's probably a better way we could deal with that. But the first thing I would do is I would go ahead and simplify the 64 over 24. We know that 8 is a factor of both of those, so we can start out by saying 8 goes into 64 8 times, and it goes into 24 3 times. So we get 8 plus 8 over 3. If we do get a common denominator, we know it's going to be a denominator of 3. So we would say 24 over 3 plus 8 over 3, and that's going to give us 32 over 3. So here the answer is D. Hopefully everyone is starting to see that, you know, we're using a lot of the same principles, although this problem was slightly different from the last one. So the next problem I want to present is one that's going to be similar concept, but instead of actually having a real integer value or numerical value for your input, we're going to see what happens when you have just a variable for your input. And as everyone probably now knows, because we've been doing this many Tuesdays, that you know, presenting variables in problems instead of real numbers is something that can happen in any topic whatsoever. So as you'll notice in our curriculum, it doesn't matter what chapter you land on, we do test you guys using variables as well as whole numbers. So why doesn't everyone start this one here? Okay, so that was about 2 minutes. So the good news about variables in problems like this is that your process shouldn't change. So we see we have f of x equals x squared plus 2x minus 1. So what that initially is again, that's the function equation that we're dealing with, but we see we're dealing with it with an input of x plus 1. Now, the good news is we can easily plug in x plus 1 everywhere we see x. So f of x plus 1, well, we're going to square that because we're plugging it in for x in all places. Then we're going to add, or excuse me, plug it in again. So we have 2 times x plus 1 minus 1. Now, this is also a good time to bring up the fact that on the GMAT, yes, we have 19 chapters in our curriculum, but what you'll start to notice as you get into harder questions is that other topics and chapters are layered amongst other chapters. So yes, we're doing exponents right now, or excuse me, functions right now, but you'll notice what this problem is really testing at its core is it's kind of testing, do you know how to deal in some ways with quadratics and foiling? Because if you see the next steps, well, we see we have x plus 1 times x plus 1, so we're going to have to FOIL that. Then, of course, we have 2x plus 2, and then minus 1. So, FOILing this out, this gives us x squared plus 2x plus 1, plus another 2x, and then, of course, plus a singular 1 here. Now, the last thing we can do is combine all our like terms. This gives us x squared plus 4x plus 2, and that is answer choice D as in dog. Okay, so those are all pretty similar questions. I always like to, use questions of similar nature, but showing you how there's different variations. In fact, this is what we do almost every Tuesday night, so hopefully everyone's seeing that the more you can kind of practice these special things or specific things, the better you're going to become. So I'm going to do one more question. This is straying a bit from what we were doing in the first 3, and then, Scott can, of course, take over. I really like this question here because it forces you to go through a number of different steps before getting to the correct answer. So I'll give everyone 2 minutes, and then we can move forward from there. Okay, so that was a bit over 2 minutes. This is a really interesting question because it does force you to, as I said, kind of really focus on the setup. And once you get the setup right, you're in really good shape. And, you know, what this question is asking based on this condition, it's saying when is f of 2x, where 2x is the input, greater than 2 times the output of f of x. Now, clearly we could use x and 2x, but it's kind of nice to get a real number here. It's going to allow you to plug into your answer choices a little bit quicker. And anytime you're choosing a number, it's strategic to use a number that's, you know, small and malleable. And I think using 1 in this case is perfect. So now the question is, when is the condition satisfied of f of 2 being greater than 2 times the output of f of 1? And so all we're going to do here is we are going to use x being 1, we're going to use the inputs of 2, and then we're going to use the input of 1 to plug into our answer choices to see which one is greater. So if we go with answer choice A to start, well, we see f of 2 is simply equal to 1/2 times 2, which is 1. We see that f of 1 is 1/2, and of course, if we multiply that by 2, we get 1. So does that satisfy the equation, or excuse me, the condition? No, it doesn't, so we keep moving. F of 2 in B is -1/4 times 2, so that's going to give us -1/2. F of 1 in B is just going to give us -1/4. Once again, -1/4. If we multiply that by 2, we get -1/2 as well. The condition is not satisfied. C, we get f of 2 equals 2 plus 4, so that's 6. F of 1 is 1 plus 4, so that's 5. We multiply that by 2, we get 10. In this case, the f of 2 is actually less, so that doesn't satisfy it. Finally, if we go to answer choice D, we get f of 2 is 2 squared plus 2, so that's going to be 6. And f of 1 is going to be 1 squared plus 1, that's 2. Even when we multiply this by 2, you see we get 4. Obviously, 6 is greater than 4, and we're right. Now, something students always ask is, well, should you check E if, in fact, you know, you got answer choice D to work? And, you know, my answer is, well, it depends how much time you have left on the test and how well your timing is going on the test. Are you ahead of the clock? Are you behind the clock? And then additionally, how confident are you in your math? You know, if you're super confident and you're running out of time, then you just got to roll with it and keep moving. If you're ahead of the clock and you're not super confident, it doesn't hurt to check the final answer choice to confirm that D is the right answer. So Scott's going to pick up from here. I think he's going to dive into some pretty challenging sequences. So Scott, I'll pass you the ball and you can take over.
Hey, thanks, Jeff. How's the audio tonight?
Great.
Great, good. Hey, everybody, thanks a lot for coming, as always. I know you have probably many more interesting things you could do on a Tuesday night, so we appreciate you hanging out with us. So what we're going to do in the second half of the webinar, as Jeff said, is we're going to look at some tricky sequences, and through these problems, I'm going to show you a lot of interesting techniques and strategies, some of which may be hiding in plain sight for you at the moment, some of which may be totally new, but at either rate, is going to be valuable for you to understand and then later go back and practice with. Now remember, if you're new here, we're always striving for simplicity. So the biggest mistake people make on the test is they overcomplicate stuff, because remember, on a standardized test with 2 minutes per question, give or take, there has to be a simple solution to the problem. Okay? Now, the challenge, of course, is finding that simple solution, but you can't find that simple solution unless you're looking for it. So the hallmark of the rest of the night and all these webinars in general is let's look for simplicity over complexity. So with that said, what we're going to do is we're going to take a look at this sequence question. And I'm going to give you about 3 minutes because I think 2 minutes, even for people who are well versed at this, is going to be a little bit short. So let's start our clocks now. Okay, guys, that's a little bit over 3 minutes. So let's take a look at this problem. So we have A, B, and C, and they're non-negative integers such that 3A, B, C, and 27 form a geometric sequence. So there are a number of different sequences that you could see on the test. In theory, there's an infinite number of them, but in practice, there's really a limited number. But there are a couple of different types of geometric sequences that are really important. And one of these guys is called a geometric sequence. Now, do they always tell you you have a geometric sequence? No. It's easier if they do. They could also give you enough information such that you could deduce you have a geometric sequence. But either way, they're a type of sequence you have to be on the lookout for. And in a geometric sequence, the hallmark is each term gets multiplied by a common multiple to get the next term. So, for example, let's say you started with the number 2, and then we went to 4, and then we went to 8, and then 16, and then 32, and then 64. And let's say we knew in the sequence that in each series what was happening is we were multiplying the prior value by 2 to get the next value. Okay, so in other words, what you can see here is take 2, multiply it by 2, you get 4. take 4, multiply it by 2, you get 8. Times 2 is 16, times 2 is 32, times 2 is 64, and you can go on and on into infinity. Now, the one thing I want to caution you to is just seeing 2, 4, 8, 16, 32, 64, it doesn't mean, that the next number is 128. It's kind of likely that the next number is 128, but in the world of math and science, kind of likely is worthless, right? So you got to actually know the rule in question that's driving the sequence. And I'm not really going to get into that tonight because that's a whole other animal, data sufficiency questions and stuff. However, it is something I want you to be thinking about. That is, you need to know the rule that's developing the sequence to actually know what the next term is going to be, because weird things happen, right? You could have 2, 4, 6, that's going to be 2, 4, 8, 16, 32, 64, 128. And it could be doubling for 1,000 terms, and then the 1,001st term, all of a sudden the sequence changes, right? So you got to know the actual rule to make a valid conclusion. But anyway, we're told here we have a geometric sequence, so we know that we have a number multiplied again and again and again. Okay, so just so we don't get confused, I'm actually going to erase this 2, 4, 6, 8, this 2, 4, 8 nonsense and get to the problem. So take a look. So we have 3, and then we have A, and then we have B, and then we have C, and then we have 27. And because it's a geometric sequence, what we know is that each time, and I'll just put it in a box, this will be our symbol for like a little multiplication. So each time we're multiplying by some number we call R. So in other words, we multiply 3 by R to get A, and then we multiply A by R to get B, and then we multiply B by R to get C, and then we multiply C by R to get 27. Now, the key is realizing where is the foothold in the problem, because the variables don't help us very much. But we can see that if we can connect 3 and 27 somehow, we should be in business pretty well. So here's the magic of the problem that I want you to see. Well, what happens is we take 3, and I don't care about any of the intermediary values. I don't care what A is. I don't care what B is. I don't care what C is. They're not necessary here. But what is necessary is to realize we multiply 3 by R 4 times. And although there are some intermediary values after each multiplication of R, at the end of the day, we don't care in this problem. All we care about is after those 4 multiplications of R, we're going to get to 27. Okay, so that's a definition, remember, of a geometric sequence. And what's the geometric sequence? Well, start with a number. That's not going to work. Let me go to a highlighter. Okay, start with a number and multiply it again and again and again by the same number, and then come up with some other number, right? Just to be super technical here. Okay, so what we have is 3 times R to the 4th is equal to 27. All right, well, that means that R to the 4th is equal to 9. And here's a point where a lot of students struggle. They're like, well, how the heck do I take R to the 4th and 9, have that equal 9? Well, just keep it simple, right? So first say that, well, we can take the square root of both sides, and we'd see that R squared is equal to 3. Now, it would really be plus or minus 3. Remember, if you're dealing with an unknown here, but we know these guys are all non-negative integers, so it's just going to be R squared equals 3. And then take the square root again of both sides, and we'll say this must mean that R is equal to the square root of 3. Square root of 3, okay? Which is no big deal. So if you take it step by step, it's pretty easy. Right, but if you just try and say, okay, what's the, R to the 4th equals 9, what's R? It's kind of complicated to do that. So anyway, the good news now is that we have the common number that's being multiplied. Of course, that's the square root of 3. All right, so with that, we can actually get all of the values in the sequence, right? We'll do that in blue. So we know that A must be equal to 3 times radical 3. We know that b must be equal to 9, right? Because that's one more multiplication of radical 3. And we know that c is equal to 9 rad 3, because that's just one more multiplication of radical 3. Okay, so we want to know what's the average of A and C. So we're simply looking for 3 radical 3 plus 9 radical 3 over 2, which is equal to 6 radical 3. And let's hope that's an answer. Yes, it is. Answer choice C. So I think that was a pretty difficult problem. I think there was a lot of stuff that you had to think about there and you had to consider. But the good news, guys, is that it really wasn't that tough, right? Like once you saw the approach, it wasn't so bad. And that's always going to be the key with GMAT questions. Okay, there's 1 or 2 or sometimes 3 key hurdles that you have to jump, and once you've jumped those hurdles, well, you're pretty much rolling. Okay, there's another question I want to do with you that first doesn't really seem like a sequence question. However, it's going to teach you some valuable things that a lot of students never really encounter to their detriment. So let's take a look at this guy. Again, why don't we shoot for about 3 minutes, and we'll start right now. Okay, guys, that was a little over 3 minutes. Let's take a whirl at this. So we have x, and it equals the sum of the first 30 positive even integers. And we have y, which equals the sum of the first 30 positive odd integers. We want to know what's the value of x minus y. So most of you don't really care why this is a sequence problem. And I'm not even going to teach it to you in the traditional sense of a sequence. So just so you know, it's why it is being taught tonight, because it technically is a sequence. But let me show you a really easy way to handle this. I'm actually going to show you 3 really easy ways to handle this. And the reason why I'm going to do that is so often I see students struggling with these types of questions. So the more ammunition you can have, the better able you're going to do with these guys, the better you're going to be able to do. So here's a really cool formula. So the sum of the first m even whole numbers, sum of the first m even whole numbers is equal to m times m plus 1. Now, I encourage you to play around with it tonight or tomorrow at some point this week, just so you're confident. A lot of students say, how can that be? Right? How can the sum of the first m even whole numbers be equal to m times m plus 1? Well, it is, but you have to believe that. So play around with that. Pick some numbers, hack around in your calculator, make sure you buy into that. Okay, so look, if x is the sum of the first 30 positive even integers, well, this is very simply going to be equal to 30 times 31, which is equal to 930, and that's, of course, the value of x. Now, sometimes students will say, well, how can it be as simple as a formula? The GMAT is not supposed to be about formulas. It's true. It just so happens that this is a formula that has sort of circumnavigated a lot of the critical thinking you would need to solve this in other ways. So this is a very handy one. Okay? Now, let's look at another formula that will handle the odd integers. So the sum of the m, and the key here is the, let me rewrite that so you guys get it down properly. So sum of the first m odd whole numbers. So the sum of the first m odd whole numbers is simply equal to m squared. And I encourage you to play around with that as well, so you have total faith that it works. So therefore, the sum of the first 30 positive odd integers, which is y, well, y is simply equal to 30 squared, which is 900. Okay, so x minus y is a gravy train, right? It's 930 minus 900, which is equal to 30. Answer choice A. So again, there's a lot of ways you could do this. You could use like the sum is equal to the average times the number of numbers, what students do, which is fine. You could use some sequence formulas, which are fine. There's a lot of stuff you could do here, but I think this is the most straightforward. Let me show you maybe a solution that's a little bit more in line with the way that they may want you to think. But who cares? It's about doing things that work and doing things that make sense to you. So here's another way of doing this that's a little bit more logic-based. So if you think about what x is 2. You guys are going to have to scroll down too, because I'm at the bottom of the screen. So x is 2 plus 4 plus 6 plus dot, dot, dot. And of course, dot, dot, dot means just that the pattern continues. Plus 56 plus 58 plus 60. Right? So the sum of the even integers up to 60. And students say, why 60? Well, 60 is a 30th even integer. Right? Because remember, they're skipping one, they're every other. And y is equal to the odds. So y is 1 plus 3 plus 5 plus the pattern continues all the way up to 55 plus 57 plus 59. okay? If we want to subtract these two, well, being able to subtract strategically in situations like this is really key. If you think about what we have, well, we have 2 minus 1, we have 4 minus 3, right? Because we're looking for x minus y. We have 6 minus 5, dot, 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 56 minus 55, 58 minus 57, 60 minus 59. So if you think about it really carefully, what's happening is 30 times you're getting the number 1, right? Because this is equal to 1, that subtraction's 1, that subtraction's 1, right? All of these subtractions yield a 1, and of course 30 times 1 is equal to 30. So that's probably like the logical analysis they're looking for. I'm only guessing. I mean, who am I to say, but just my own conjecture. Okay, but again, you see 30. And let me actually give you what may be the most sophisticated way to do this. So one more way to do this. Okay, well, we said the sum of the first m odd integers is m squared, and the sum of the first m even whole numbers is m times m plus 1. And I'm way at the bottom now, guys. Well, we're looking for the difference between those two, right? So we're actually looking for m times m plus 1 minus m squared. Well, that's m squared plus m minus m squared, otherwise known as just m, right? So if you think about this, the answer is already given in the question because the difference has to be 30. If you're looking, if the number is 30, right, 30 positive even integers, 30 positive odd integers, well, strangely, but sometimes kind of magically, the difference would have to be just 30. Okay, because it's 30 numbers here. So 3 powerful techniques, and as you're doing like MBA.com problems, you're going to see these. Who knows? You could see these on the test. It's tough to say. You'll definitely see them in our curriculum. And we're going to do one more problem, but take a minute and look at this. And as you're copying down your notes and as I'm finding the next problem, just remember, the definition of insanity is doing the same thing again and again and expecting different results. And every day, every week, you know, I see students who are using materials that are not getting them results. And I think that's kind of becoming my slogan of the year is, why are you using those materials? So keep that in mind. If you are not getting the results you need from the materials you are using, why do you want to continue using them? So let's see. Just looking for the problem I want you guys to do. It's hiding on me at the moment, but we'll find it. It can't hide. Okay, here it is. Okay, so this last one, guys, it's another sequence, but it's going to integrate in some really important number property concepts. So why don't we take this away, and we'll set our clocks for 2 minutes starting now. Okay, guys, that's about 2 minutes or so. Let's give it a whirl. So it says, in the sequence above, first term is m. Each term after m is equal to twice the previous term. For any value of m, the sum of the first 6 terms of the sequence is divisible by all the following numbers except. Okay, so the first 6 terms are going to be m, 2m, 4m, 8m, 16m, 32m, and that's it. So those are the first 6. So if we sum those guys, what do we get? We get, it's like 63. Yeah, we get 63m. That's the sum of the first 6 terms. So students tend to say, well, great. Well, why is that important? Well, it tells you something really important. If something is 63m, and m is an integer here, right? Well, it tells us that the sum of the first 6 terms must be a multiple of 63, because 63 times any integer is a multiple of 63. With that, we can look at the answer choices, and we can say, well, 3 is a multiple of 63, so that works. 7 is a multiple of 63, so that works. Remember, this is an except question. 9 is a multiple of 63, 21 is a multiple of 63, but 5 is not a multiple of 63. So this question, as many GMAT questions, blended a couple different ideas here, one being the idea of sequences, one being the idea of number properties. So I hope that was helpful for you all. As Jeff said, thanks a lot. If you have any questions, give me a call, give me an email, same for Jeff. I really encourage you to sign up for a trial with our new course. It's truly a phenomenal, revolutionary, it's a radical way to study for the test. I'll be shocked if you don't find it's the best material you've used. So we'll look forward to seeing you all back here again, same time, same place, next Tuesday night. And we'll pick another interesting topic for you. And we appreciate you coming and hanging out with us tonight. Take care, everybody. Good night.